we're very delighted to have Jürgen Jost here from the Max Planck Institute for Mathematics and the Sciences, of which he's the director. Jürgen has done a great deal of work on the interface behind mathematics to machine learning to many scientific problems, and low-dimensional structure of data problems and the mathematical structure of networks and the like. And today he'll tell us about data visualization. Please.
Yeah, thank you very much for inviting me and giving me the opportunity to present our work here, and in fact, even as a first speaker. So among the three affiliations that are listed here for this talk, the second one is the most important one. That is a federally funded German project on AI and machine learning. And my group there is working on the mathematical foundations of that, and I will present what we are currently doing. And so the question, as you all know, is you have some data set, high-dimensional data set. You don't know what it means. You don't know what it is. It may be noisy or whatever, and you want to find some structure. And some way for finding structure is to try to represent it in 2 dimensions, to project it to 2 dimensions. Of course, if you just simply project it, you will not see anything. And typically, if you do a linear method like PCA, if I'm on a PCA, you will not see that much either. But now in recent years, more sophisticated nonlinear techniques have been developed. And that is also what we have been currently working on, building on my own background in geometry, which comes in quite handy here. So I cannot advance the slides. Perhaps I do it here. Doesn't work either. Okay. Here. Well, this was too much already. It's kind of slow. Okay, here. Oh, so the picture doesn't come out too well. What you're supposed to see here is a visualization, a 3D visualization of a mammoth, or some kind of ancient elephant. And so just want to illustrate it so that you already see the original picture, but somehow we want to represent it in 2D in a way that is not like this projection here, but that sort of gives a better glimpse of the structure. So here is one technique that does it, that is called UMAP. That is called ISOMAP. Yeah. So you see already something, namely that the limbs, the trunk and whatever are spread out in different directions. So that is something that is in principle desirable. Now here's another one, that is UMAP, that is currently the most popular scheme in data visualization and clustering. It looks a little distorted, unfortunately. I mean, it doesn't come out that well on the screen here, so I apologize for that. And now I present our method here, which we call ISUMAP, for reasons to be explained later. And you already see what it achieves, namely the hind legs, the front legs, the trunk, and the tusks and the tail, and everything is spread out in different directions. And that is something desirable for the visualization, namely that you separate the individual features. And so you already see my collaborators here. So that is a group that I have at SCATS AI in Leipzig. And we have some papers, but we also have written a book about that. I mean, I, as a mathematician, like to write books, actually. And so that will come out within the next couple of weeks. It's essentially ready to be sent to the publisher. So that is kind of as an introduction. So as I already said, data are often given in some high dimensional, typically Euclidean space. Of course, what we see was 3-dimensional. Yeah, but if you are in biology, if you talk to biologists and they measure many features or so, or if if you look at semantic networks or so, then you have 300-dimensional spaces typically, and you want to represent these data. And what is good for us as geometers, typically have distances. Whatever the distances come from, typically you evaluate certain features, and then you just add up the distances between the differences of the feature values or whatever. So the important thing is that we have metric data. And now, even though they come in some high-dimensional space, all natural data carry some intrinsic regularities and correlations. So that means that they're intrinsically lower dimensional. Even though they're situated, whatever, in a 300-dimensional space or 1,000-dimensional space, intrinsically they're much lower dimensional. And we want to bring that out in the first place. That is the first step. And these are schemes that were already introduced 20 years ago, manifold learning or so, to identify them. And then we want to further project them down onto 2D in order to visualize them. And since they have these regularities and correlations, they may naturally be assumed to sit on a smooth, lower dimensional manifold in that high dimensional space. And that is quite important. The concept of a manifold offers us a way to interpolate. Now, if you have a couple of data points, we want to see what is in between, then somehow if we know the structure of the manifold roughly, we can interpolate. Yeah, so the important assumption here is that we do not have singularities, because if we sample points, then from some structure, singularities are typically lower dimensional. Every geometer knows that. And so if you randomly sample points, you will typically miss the singularities, you will not see it. Yeah, and so therefore it is important for us to have the assumption that we are on a manifold. But of course, the manifold need not be linear, otherwise things would be trivial. Even though it is lower dimensional, it may be highly curved and therefore stretch into many ambient directions. Even a one-dimensional curve in 300-dimensional space can in principle spread into all directions. Yeah, so we need to account for that. And also there's some problem that previous schemes often had. They were assuming that the data was then uniformly distributed on that manifold, but that need not be the case. And the method that we have developed is particularly designed to handle that issue. And as I already said, we want to ultimately visualize them in 2 or 3 dimensions but preserving the qualitative aspects like clusters, but also local structures as well as possible. So there are some existing methods. ISOMAP, that was already introduced a quarter of a century ago. Then there is this TISNI, which is stochastic neighborhood embedding. That is what SNE stands for. And there is the currently most popular one, UMAP, universal manifold approximation and projection for dimension reduction. And our aim was to improve, in particular on the latter one. Yeah.
The pointer. Right, towards that will work.
I need to point it towards the computer. Okay, so I get it. Of course, I may forget it. You may have to remind me again when I get excited about the talk. I forget these technical details. So the first thing in UMAP and all our scheme is to get at the local structure. So we connect each point with its k nearest neighbors, and so that we get a star graph. So the point itself is at the center, and the peripheral vertices are the nearest neighbors. So that is the local thing that we want to preserve. And then now we have these local star graphs, and they need to be merged again or glued together again in order to have a global structure. And for that, in UMAP, tools from category theory have been used, and in particular that was they drew upon the work of David Spivak. I think he's also somewhere in the region here. And then one projects the resulting thing onto 2D with minimal distortion. Okay. So now that's the background. We have the concept of a Riemannian manifold already in the middle of the 19th century. So that means we have a manifold, and this is equipped with a metric tensor, which allows us to measure angles and distances by having scalar products at each point. Of course, the important idea was that such Riemannian manifold need not be realized in any ambient Euclidean space. And so we don't need to assume, in fact, that our data are sitting in some Euclidean space. That is just a typical case that you have when you deal with data. And the important concept there was a curvature tensor, which is computed from second derivatives of the metric. But somewhat surprisingly, now in the beginning, we will not really need the curvature tensor. But of course, as a geometer, I will try to bring it in at the end again. But Riemann introduced another important device, namely that of normal coordinates, and that is kind of inspiration. So you sit at a point that might be a sample point for our data, and then you look towards the other points, towards the points in the vicinity, because only there you have a unique geodesic, unique shortest connection. So you are sitting here, and then there are other points distributed in the vicinity, so you measure how far they are away. And so that is kind of the inspiration that we are also using here for our star graphs. Of course, this is essentially the same as Euclidean polar coordinates, but we shall even forget about the angles. But of course, we can do that also in a discrete metric space. So we have a point, and then we construct the star graph, as I already mentioned, connecting it with its k nearest neighbors, and we are assuming that our sample is dense enough so that we are really in a local vicinity there, so that the conceptual schemes of Riemannian geometry apply. But as we shall see, we need to modify the metric. Just taking the global structure of the metric and projecting it doesn't give the best possible results. Also, the original scheme, ISOMAP, essentially did that.
How do you choose K?
That is up to you. You can experiment a little with that, and I will later on show you, if time suffices, a couple of slides where you see what difference it makes to choose different K. If you choose K too small, then you don't get enough structure. If you choose K too large, then you're beyond the local vicinity. So now we are modifying the metric. So D is the original distance. Pointer here, well, I can point that way. So X is the point that we are looking at. X1 up to Xk are its k nearest neighbors. They are ordered according to distance. So X1 is the closest neighbor, X2 is the second closest neighbor, and so on. And so we subtract something there if we want, and we normalize it by a constant. And for all points that are outside this local neighborhood, we just put the distance to be equal to infinity. To first concentrate on the local picture. And in UMAP, even one puts the distance here equal to infinity, but then you are in a situation where the triangle inequality is no longer satisfied. So we rather did it that way. So that should be an X here, sorry. So now we need to choose and rho and sigma, and I will tell you in a moment. Hopefully the slide didn't appear. Right. So we put rho of x equal to the distance to the closest neighbor. And so rho of x either is put to 0, but in high dimensional space it might be better to put it equal to the distance to the closest neighbor. The reason is that in high dimensions, if your sample points from a ball in high dimensions, they're almost all they're typically close to the boundary of the ball, because of the volume expansion. Yeah, and so therefore you want to normalize that a little bit to handle the curse of dimensionality. Yeah, in other words, in high dimensions, the distances from the center to the k nearest neighbors are very, very close to each other typically. Yeah, because the points are sitting close to the boundary. Yeah, and therefore you may want to subtract the distance to the first nearest neighbor.
This tries resulting distance between x and x1 will be 0.
Yeah, sure. I mean that is one aspect there. It's no longer really a metric. It's a degenerate metric. It's degenerate for two reasons. So something can become 0 here, and something can become infinity. Yeah, and sigma x is a normalization factor. For example, you can divide by the distance to the kth neighbor, because if the data are not uniformly distributed, you want to make them a little more. You want to make the star graphs as uniform as possible, so you normalize them. Yeah.
Excuse me. Do you begin with a metric that is for these nearest neighbors xi, xj, and xl? Do you start with a distance for them?
Yeah. Well, I mean,
replace it with this other distance.
Yes. I mean, these the original distance functions that we have on our data set.
But it's given to you on all pairs of x.
Yes, sure.
So can you explain why you create these localized metrics around each point rather than just taking the initial metric?
Right. So there are many reasons for that. So if the points are sitting on a manifold in some high dimensional space, and the distance that you take typically would be Euclidean distance, which is not what you actually want. Yeah. And so therefore you should first of all localize things. One could use a path distance, by making a graph connecting points that are sufficiently close to each other, and then looking at the path distance. And that was in fact the original scheme introduced more than 20 years ago, but the performance and the visualization was not optimal. Yeah, and so therefore people came up with the idea to normalize the local distances first, to concentrate on the local aspects and have the best possible representation of the local picture. First of all, to handle the curse of dimensionality. Yeah, because as I said, the distance to the k nearest neighbors are typically within a rather small range in high dimensions. Yeah, so you normalize it that way. And then secondly, the data need to be uniformly distributed on the manifolds, and certainly they might be sparser, and in other reasons they might be denser. And in the beginning, you want to handle that to make the local geometry more uniform.
Just a question on your third line in your formula. To me, it would be more natural to multiply the right-hand side by 1 over the square root of 2. That would incorporate the assumption that the two nearest neighbors are roughly orthogonal, which would be typically the case.
One could. I mean, we have not tried that, but
the reason I ask is what you've written there tends to make them diametrically opposite.
Yes.
What's the point of that? That doesn't seem to correspond to anything.
I mean, as in the original UMAP scheme, this distance was even put to infinity, to really concentrate on the local aspects. So we modified that step, but since we really want to see what it looks like from the sample point x, yeah, and not having any other relations there. We choose that one just to have the triangle inequality realized. Of course, we could make it shorter, but of course the points might sit in opposite directions. But of course, as you're pointing out in high dimensions, they will typically point into different directions. So one could modify it by some factor suggestion, but I have to admit we have not tried that. Yeah, I mean, good point. So it might be worth trying that out. Okay, so I explained already all that. So now we have these local structures and we want to recombine them, combine them, and that is the point. And so now we, in the UMAP scheme, with the ideas of David Spiegel behind that, people turn to category theory. So they turned this local structure of the star graph into something different, a so-called fuzzy graph, which I will explain in a moment. You have these fuzzy graphs, they can be merged in a more or less canonical way with the help of a T conorm, which I will also explain. And in fact, that works not only for graphs, but that also works for simplicial complexes. And since I want to make connections with other schemes, I will also introduce that. So now let's go a little into category theory, into different domain. So you have a basic set X, and the elements are present with a certain degree of probability or with the membership strength going from 0 to 1. So 0 means certain absence, so the thing is not really there. That will later on correspond to our infinite distances. And 1 means certain presence. So after all, the sample points by themselves should be naturally there, but the connections might be absent. So now we have this unit interval. For formal reasons, we consider it as a topological space where the open sets are just the intervals from 0 to A, open at A, and I itself. And we have the inclusion, so that A maps to B, because if something is present with a higher strength, then it also is present with the lower strength, because later on we will be looking at sheaves, so we need to reverse the arrows. Yeah. So there are fewer elements with a higher strength. Yeah, but of course, if the higher strength have a higher probability, then also they have that lower probability. Yeah. So if something is there, certainly, then it's also there with the probability at least one half. So we call the points with members strengths at least A, X of A. And as I already said, if A is less or equal to B, then XB is a subset of XA. And so therefore, such a fuzzy set can be seen as a pre-sheaf, or in fact, even a sheaf on that interval by just assigning the set XA to the interval from 0 to A. Yeah, and so that naturally satisfies these properties. And you can also do that for higher order simplices. As said, that will be useful towards the end. And so you have an n simplex that has n plus 1 vertices, and for simplices or for simplicial complexes, you require that also all subsimplices are contained in it. And so then, I mean, in categories, you have the simplicial index category, you have that base simplex, and then when you have a triangulation of a manifold, you assign to every simplex, subsimplex of delta as the corresponding ones in your triangulation. And so simplest set then is also considered as a sheaf on that simplicial indexing category. And so to each such abstract n simplex, the set of concrete n simplices is assigned in a triangulation and in a way compatible with the morphisms, in particular the subsimplex relations. And so these latter simplices therefore need to be glued together along shared faces as in a simplicial complex. So probably you all know what a simplicial complex is. There's maybe this way of looking at maybe a little unfamiliar, but the point is that you can then also do that for fuzzy. You can define fuzzy simplices and fuzzy simplicial sets. Then you have both the simplicial index in category, and you have this I, this open interval where you assign membership strengths. And so the point, of course, is when you have a simplex with a certain membership strength, then all its faces need to have at least the same membership strengths. That comes out from the formal rules of the category here. So that is important point. You have simplices with certain membership strengths, and if a simplex has a membership strength A, then all its faces need to have at least the same membership strengths. Because if the simplex is there, then also all its faces have to be there. So now we want to represent these simplices, but the important point is that we now also have some dependence on A here. And this is, of course, otherwise a standard geometric representation of a simplex. And so this depends on this parameter here. And we just need some monotonically decreasing function here. Yeah, so A equal to 1 corresponds to 0 when everything shrinks to a point, and A equals 0 corresponds to infinity, then the simplex is infinitely large. Yeah, and for those who know topological data analysis, so Riemannian complexes, I will come back to that again. You should think of it in those terms. Now, for a small radius, you have a small simplex. Yeah, and for a large radius, the simplex when you increase, you let the simplices occur when you increase the radius. Yeah. And so that's what is underlying here. Yeah, small radius gives you a local structure. So the thing is there, Riemannian complex with a high probability. But in order if you want to increase the radius, somehow you say that your probability gets smaller and smaller, and then you have larger and larger simplices. Yeah. I don't know how familiar you are with topological data analysis, these Riemannian complexes. If you are, then it's helpful to think about it in those terms. Otherwise, you just take it as a decreasing, as a mono, I guess.
So this is kind of like a soft max. In other words, it's not, the probability of the simplex being there goes down as it gets larger.
It's larger.
Rather than in persistent homology, usually some cutoff is taken.
Yeah, of course, you can take a cutoff for practical purposes, but for our point here, of course, is since certain distances are infinite in the scheme that I described, you really need to go to infinity here. Yeah, of course, for practical purposes, in TDA, you take some cutoff because if your data set has a certain diameter, there's no point going beyond the diameter. So, as I already said, we identify A with the membership strengths, and the larger A, the smaller this geometric realization is, and A equal to 1 corresponds to a single point, whereas the space for A equal to 0 is infinite. Yeah, and so this then brings in naturally into the category of Uber-metric spaces. I will define that in a moment. That I don't know. I think David Spivak introduced that notion. I don't know why he chose the name Uber. I mean, I have an Uber app on my phone, but I'm not sure whether that was his motivation. So an Uber metric space is a metric space where distances are allowed to be both 0 and infinity, but where the triangle inequality is still supposed to hold. Or there's a category of extended pseudometric spaces, where if some distances are infinite, then the triangle inequality is no longer required, and that is what is used in the UMAP scheme. But we use those supermetric spaces here. And so we have a fuzzy simplex. Yeah, we have this A, and then we construct this geometric realization here depending on A, and that gives us a functor in terms of category theory. And we can also go, of course, in the other direction. If you have such a simplex with a certain distance, then we convert it into a fuzzy simplex according to the opposite rule, and that is also a functor, the so-called sinc functor realization and sinc functor. And then you prove that the sinc functor is a right adjoint of the realization functor. And I mean, we had to go carefully through the category theory, because in the literature it was stated the opposite, namely that this is a left adjoint, but this is not true. So let me recall, for those who are not so familiar with category theory, two functors between two categories, or categories now are the fuzzy simplicial sets and the geometric simplices, simplicial complexes. But in any case, so you have two functors. One is the left adjoint, and one is supposed to be the right adjoint of the other. So this is a relation between two functors. And here, this one F appears on the left, so that's why it's called the left adjoint. So if you go from A to B, map A to F of A, then the homomorphisms in the category between F of A and B correspond to the morphisms when you go the other way. You go from this G from B to A, and then you have the morphisms here. And so the concept of an adjunction is useful, because then you can essentially go back and forth between the two categories and transfer structures from one category into the other. So, as I already said, the sinc functor is a right adjoint of the Riemann functor, and so this is useful for our purposes, even though in the end it is not really necessary, but it is inspirational. So we have these generalized metric spaces, these Uber metric spaces constructed from our star graphs, and we want to merge them. Yeah, and so therefore conceptually one goes to these fuzzy graphs or fuzzy simplicial complexes where one has some way of merging them, combining probabilities, and then one goes back in order to have the geometric realization of our data set. So recall, we had constructed the star graphs centered at the sample points, connecting them with the k-nearest neighbors, and essentially relegating everything else to infinity. Now, when x and y are both among the k-nearest neighbors of each other, then some of the distances, or if we convert them into probabilities, the weights of the corresponding edges of the corresponding edge are in general different, because we normalize them in a different way. And although you should realize that this k-nearest neighbor relation is not a symmetric relation. If y is among the k-nearest neighbors of x, that does not necessarily imply that x is among the k-nearest neighbors of y. Yeah, because the distribution of the points is not necessarily uniform. Yeah, but then we normalize things by the sigma of x that depended on the center. And even though if they're both among the k-nearest neighbors of each other, then in the two star graphs, the weights or the distances on the corresponding edge are different. And so we need to merge them again. But now we convert the distances into probabilities, membership strengths, and for probabilities, there's a natural way. There are natural ways of merging. Now, it's not unique. Yeah. So there's a question that you have asked already, so was very good. Why don't we simply construct a graph from the sample by connecting sufficiently close points and use the original distances? Or we connect 2 points when at least one of them is among the k-nearest neighbors of the other. Well, as I already said, one of the earlier schemes, ISOMAP, essentially does or did that, but the results become better and you use a apparently more complicated procedure suggested in UMAP, which we have then refined. So this captures the local structure and the possibly varying density better, as I will show later. So we had converted the star graphs into fuzzy simplicial sets, and so the edge weights have become probabilities. And so now we can use schemes to combine different probabilities on the same object. So as I already explained, the edges in general will have different probabilities. In fact, some of the probabilities may be even zero when for one star graph the edge had the distance infinity, but it may also be possible that both are finite numbers, but they can still be different. And so therefore we need concept of a T-conorm. So here from 0, 1, cross 0, 1 to 0, 1, so probability here, and you want to create a joint probability. So it should satisfy certain axioms, it should be symmetric, it should be associative, it should be bounded from below. One of the probabilities is 0 and the other one is A, then you want to have A. And of course, it should satisfy some monotonicity conditions. If both probabilities are larger, then also the final combined probability should be larger. So just to make you a little familiar with that, it's easy then to prove this relation. If one of the probabilities is 1, then there is the combined probability also has to be 1. First of all, T of 1 and 0 is 1 by this relation here. Then we use the monotonicity. If we increase that one here from 0 to some other value, it cannot become smaller. But of course, 1 is a maximal value. And of course, this is symmetric to also get the other relation. Yeah, so just to familiarize you a little with that concept to prove that basic result. But nevertheless, the choice of T is not unique. One choice is simple choice. I will give you some other choice later on, but the one that we are using is simply we take the maximum of the two probabilities. But if you get bored with the rest, you can try to figure out other choices in between. So now with the T-conorm, we can merge fuzzy simplicial complexes by just merging the probabilities on the same underlying set in a symmetric and associative manner. That is precisely what we want to have for our star graphs. So now with a maximum T-conorm, this is pretty simple. So we have different star graphs. We identify points when they correspond to the same sample point. But then we can go, in order to get the distance, we can go to a family of star graphs. And so we just try to find that family of star graphs going from one point to the other. That's the sum of the distances, the smallest possible one. It may be that things are completely disconnected, and then the resulting distance will be infinite. That is a possibility. Might be good for clustering, but for most typical data sets, you have some kind of cohesion, and then you usually get finite distances. So, as I already said, other T-conorms yield different results, and we can experiment which one works best for a given data set. So again, according to some questions, there are some free parameters there in the scheme, even though category theory is meant to make everything completely canonical. That is not really the case here. So the number k is a free parameter, the number of neighbors that we choose. Although we are not necessarily required to take minus logarithm as a monotonically decreasing function, but we have not really experimented much with that. But the choice of the t conorm is also a parameter that one can experiment with. And we have, in our data, we have tried a couple of different ones. So now our scheme, let's summarize it. So we have a sample x1 up to xn from a metric data set. As I described in the beginning, we construct this star graph centered at the xi, this Uber matrix that assign distance infinity between different points, unless they are among xi and its k nearest neighbors. Yeah, and these metrics are normalized to adjust for non-uniform distributions of the samples and to handle the cost of dimensionality. That was the first step. The second step is then merge these local star graphs conceptually by converting them into fuzzy graphs and use the t conorm for combining probabilities, even though the geometric scheme that I described in the end didn't really require to go through category theory, but for general conceptual reasons, as I will try to explain later, that is nevertheless useful. And I must say we got a little carried away by the mathematics, and so we were happy to work also on those aspects. Now, then next step, there's a time-honored algorithm, the Dijkstra algorithm, to compute the distance function on the resulting global graph. So we've merged all of them, so we get a global graph with weights, and so then we need to compute the distance between 2 points on that graph. There's an algorithm, the Dijkstra algorithm, that does that, but that, for all the schemes, is the one that increases the algorithmic complexity and increases computational time. So that is the computationally most expensive step, even though if you think about it mathematically, that looks rather trivial. And then now one approximates it by a 2D graph. So there are schemes for doing that. We have chosen multidimensional scaling as in the original ISOMAP algorithm. Yeah, so we just try to construct a two-dimensional graph so that the distances match as well as possible. Now, UMAP used a different scheme. So they try to minimize some Kullback-Liebler distance there, but according to our experiments, this one works better. It's called multidimensional scaling in the literature. And there are also variants there. You can modify the loss function here.
A two-dimensional graph means a graph embedded into.
It was a good point. Yeah, so we want to have a graph in the plane. Yeah. All the yi are supposed to be points in the two-dimensional plane, but then we want to match distances as closely as possible. And so for simplicity, we just look at this loss function here, but you can take other loss functions. And again, you can experiment a little. Now let's see some results. So this is to show the result of non-uniform distribution. So we have a hemisphere here, and the points are denser towards the North Pole here. And so here is our representation here that really uniformize the things. So you will no longer see that the distribution is not uniform there. Of course, depending on your task, you may or may not want to have that. Yeah, but for most data sets, I think it's good to handle the fact that the data sets are not uniformly distributed. This is the original isomap here that projects things here. So you see the cluster here. And that is UMAP here that gives a slightly distorted picture. So the boundary effects here that causes somewhat rugged structure at the boundary.
Why does C have that cluster?
Excuse me?
Why does C isomap of that cluster in the middle? Number C or letter C?
Yeah. Well, I mean.
Why is it dark in the middle?
Yeah, well, I mean, it's denser over here at the North Pole, and if you represent it as it is in the two-dimensional plane, then you naturally get denser structure also there. So isomap was, as you originally suggested, you just connect close enough points on the manifold, you have a global graph, and then by multidimensional scaling, you represent that global graph on the plane.
I see, so in A, it's not just the edge of regression that makes it look denser at the edges, it's.
No, no, I mean, it's really the fact, I mean, the two effects here I didn't really talk about. So the boundary effect, I mean, if you look at the distribution of nearest neighbors near the boundary, it's somewhat different than in the interior for obvious geometric reasons. But the point I want to draw the attention here is that here the points were more densely distributed than over here, and that is represented here, but that is uniformized over here.
It's also the optimum multidimensional scalings that we get.
Yeah, well, it's not quite a projection, yeah, because I mean we have the distances over here. We want to match them as closely as possible over here. Yeah. Yeah. It's
Not a general projection, but.
yeah. Well, I mean that is what I tried to explain with the mammoth picture in the beginning. The mammoth picture will come again in a moment. You don't just want to project that high-dimensional thing. You want to represent. You want to stretch it out on the plane. Yeah.
But the number of points in B and C is the same.
Yes. Now, so here we looked at different T conorms. Yeah. So here's you can take the algebraic sum A plus B minus AB. You can take the maximum that I did already before. You can also take the minimum, and there's also a choice of a drastic T conorm where you just put T of AB equal to 1 if both A and B are positive. And in fact, this choice of the drastic T conorm in that case leads to apparently to the most uniform result. But this is not the case for all data sets. Yeah, so as I wanted to point out, there are certain degrees of freedom in there, and you need to get some experience with your data set to see which one actually works best.
Could you remind us what this U norm is for the bottom row? It creates the bottom row.
Yeah, and then in the bottom row, you have UMAPs as the original scheme that we try to improve upon. Yeah, this is our scheme, ICUMAP, and this is the original UMAP scheme.
So not in this multidimensional scale.
Yeah, well, I mean, we apply multidimensional scaling, and we have different constructions of the local star graphs. Yeah, yeah. So UMAP is more drastic because, as I said, it even puts a distance between two peripheral vertices in the star graph equal to infinity. So it really focuses on the local thing, and so it is kind of better for clustering. If you want to have clustering, then this drastic way of doing things is superior. But if somehow you want to get a better handle or understanding of the local structure, then not being so drastic leads to better results, as I tried to show over here. So now we don't do this. We don't subtract the distance to the first nearest neighbor. Yeah, I mean, no, we had a three-dimensional picture, so we're not really suffering from the curse of dimensionality, and so in that case, it might be better to not subtract that, and so then again we use different T conorms. Maybe I shouldn't go too much into the details here. So now here is again our mammoth picture. Yeah. Unfortunately, it's not really well visible. We have this three-dimensional structure here, it's just projected onto the plane. Of course, in 3D, we are used since Renaissance paintings, what a projection, what optimal linear projection looks like. But that is not the most natural thing in order to display the features. So you really want to stretch out things. You want to realize that the hind legs and the front legs, and the tusks and the trunk and the tail go into different directions. Yeah, so that is the aim here. And so that is our scheme, that is an ISOMAP scheme, and that is a UMAP scheme, as I had already explained in the beginning. I just want to remind you of that picture here. Now let's look at some other pictures. We have the so-called Swiss hole. With a hole, there's a hole in there that is not really well visible in the three-dimensional structure. You have this curved thing, but there's a hole in there, and here you have a torus. And so you have the different representations again. So the original ISOMAP gives kind of the smoothest representation here. UMAP tries to find clusters and distorts it a little, and our scheme is kind of in the middle here.
Can you explain where the topology comes from? The roll is contractible, but those pictures on the right have a definite circle in them.
Yeah.
Like going from A to B.
Yeah, well, I mean, as I said, they're supposed to be, this is not really visible here. If you unroll it, then there's a hole in the
Oh, there
data.
is, okay.
Yeah, and so that is of course what you want to represent, and every scheme actually does that. Yeah, so there's some way of getting it at the topology. And as I said, UMAP tries too much to cluster things actually. Yeah, and for these pictures it's not good. In some other pictures, of course, it's good. I mean, if you look, for example, at the MNIST data sets, it is this handwritten digits, of course, and then you want to cluster them. Yeah, and so the UMAP actually does a pretty good job. Now we looked at many empirical data sets. So here we looked at a relatively recent one handled by the group of Ulrike Tillmann and Heather Harrington. So they looked at protein data, and the biologists speak about knotted proteins. For mathematicians, they're not really knotted, because I mean you have a string, and the string you can of course always pull straight. But nevertheless, for biologists, it makes a difference whether it's highly convolved, which they call knotted, and that makes a difference, of course, for the function of the protein, how it can interact with other proteins, what is the exposed site, what is hydrophilic, hydrophobic, and whatever. So the structure does make a difference, and biologists want to have them classified. Yeah. And so people, this group on whose data we are drawing here, use TDA methods, topological data analysis method, which I explained, and then applied UMAP to the data. So they got these pictures here, so you get some good clustering, but our method sort of gives you better view of the local structure there. How the proteins are in the vicinity of each other, and as you also see here, again, it's not very clearly visible. The color here and the color here is the same, so the clustering is not really perfect. Here you see that, of course, certain ones here are in the vicinity of those from the other class. And now we are going to collaborate more closely with biologists to handle the data. In that sense, these are just preliminary results. Here's another way of representing them, and maybe here what I just said comes out more closely. Before that, we had just the different protein classes. Now we have that the degree of knottedness here, to the extent that the biology classifies them deeply or highly knotted ones as opposed to shallow ones. And again, here, these two classes that should be separated on this class with the same color that should be in the same cluster is not really represented in the same cluster. Here we see why this is so, namely some of them that belongs to this cluster are closer to the other one in terms of the representation of TDA. I mean, you have these barcodes there, you compare the barcodes and try to cluster them accordingly.
Are the colors some other empirical label? Or?
No, I mean, the colors are just the biological labels. Yeah. So here in the first picture, this was just for protein classes. Yeah, and here it's according to the degree of knottedness, to the extent that the biologists classify them. But now, since I still have a few minutes, let's go a little more into theory. So we have these fuzzy simplicial complexes, and that's what I said. We had the fuzzy graphs, but instead of fuzzy graphs, we can look at fuzzy simplicial complexes. And so David Spivak suggested that. I mean, I already explained how to go from the heterostrips complexes of topological data analysis to those fuzzy simplicial complexes. So the larger the simplicial complex, the lower its probability. That is essentially the idea. And now you have the truncation factor that deletes all simplices of dimension bigger than 1. Yeah, so we have simplicial complex, and we just turn it into a graph, forgetting about all the higher dimensional simplicial, so about all the higher simplices. And that truncation factor has a right adjoint. Again, there's some confusion in the literature about left and right adjoints, but we worked it out carefully. So you fill in simplices whenever all its vertices have mutual distance less than this given number, because we want to look at this expanding family. Yeah. And so this now leads a family of fuzzy simplicial complexes that corresponds to the Viator-Strips complex of the original metric space. Probably you know what the Viator-Strips complex is. I will define it in a minute or so, because I still have 5 minutes. No, but now, somehow as a geometer, I want to come back to curvature. I felt unhappy about the way that curvature is not really present here, even though that is the most important, most basic, most fundamental, most important concept in geometry. So what does curvature have to do here? Now, to recall from Riemannian geometry, if you have Riemannian metric, you compute its sectional curvatures. That is, you evaluate the curvature tensor on 2-dimensional planes in the tangent space. And when you know all the sectional curvatures, then the metric is completely determined up to isometry locally. Now, that was the fundamental insight of Riemann. And of course, then you can have standard model spaces, a flat space when all curvatures vanish, the spheres when all curvatures are the sectional curvature, the same positive constant, and hyperbolic spaces when all the curvatures give you the same negative constant. And of course, then in geometry, you use them as comparison spaces. And if you have curvature between 2 bounds, somehow you want to conclude that the geometry is somehow between the 2 extreme cases, and that has been a driving research question in Riemannian geometry for a couple of decades. But I'm not talking about Riemannian geometry. So in particular, you had space of non-positive curvature, and you compared them with the geometry of Euclidean space, and you found that in many respects, the geometry of those spaces is even better than that of Euclidean space, because you have better convexity properties. Well, now here, triangle in space of negative curvature is thinner than in Euclidean space. So that is what a triangle in hyperbolic space looks like, and somehow it's thinner, curved more inward. Yeah, and when you make the curvature more and more negative, let the curvature converge to minus infinity, then get thinner and thinner, and then it converges to a tripod. So, and in fact, this is a local property that is characteristic for negative curvature. Now, then we are dealing after all with metric spaces that are more general than Riemannian manifolds, even though Riemannian manifolds were in the background. But the metric space we have, so this is a discrete metric space with distance between data points, and so still we want to have something similar. And then you can connect points by geodesics, shortest geodesics, which we cannot in our discrete metric space. But if you could, then you can still speak about geodesic triangles being set. So now we have developed a notion of curvature even for the discrete spaces, and here's a basic question: how to distinguish a tripod from a triangle? Sounds naive, simple. Tripod, as I said, is kind of the extreme case of the most negative curvature, and this somehow is suggestive locally of positive curvature. So now we assume that the distances between the 3 points, x1, x2, and x3 are the same. They are all equal to 2r. And so then we look at those points that are at distance at most r, and they intersect pairwise in each graph. So here we have a single intersection point M, which has distance r from any of them. Here this point has distance r from this one and from this one, but of course not from the other one. And as I said, in the tripod, we also have a triple intersection. All the balls of radius r and the distances between the endpoints are 2r intersect in a single point. But if we want to get a triple intersection in the triangle, we have to go to twice the radius, the original distance. Here we only need distance r in order to get a triple intersection. Here we need distance 2, radius of the ball 2r in order to get a triple intersection. So that is the difference that we are capitalizing upon. And so this is I'm suppressing some technical details here, but the point is you ask which is the smallest factor lambda in order to get triple intersections. Of course, it cannot be smaller than 1 by the triangle inequality, and you can also show that in general, at least in finite dimensions, it's at most 2. Yeah, and so somehow we say that the curvature is the more negative, the smaller lambda is. Yeah, I mean the precise formulation is a little more complicated, but that is the idea. So here we have balls in Euclidean space. So we have pairwise intersections, but we don't have a triple intersection. Yeah, and we can even associate as one usually does, one associates a check complex there. So the balls are the vertices of the check complex. You connect 2 points if the corresponding balls have an intersection. You fill in a triangle if you have a triple intersection of the balls. But here, of course, there's no triangle there. So, but then there is a contrast to Vietro-Srupps complex that I already alluded to. You fill in the triangle anyway as soon as you have the pairwise intersections. So in general, the check complex and the Vietro-Srupps complex are different from each other. That is the point here. Now, there's a class of spaces, hyperconvex spaces, that were already introduced by Aronshine and Panich-Bhakti in the 1950s, where you have this probability. If you have a family of balls, xi and radius ri, and if the condition for a pairwise intersection is satisfied in the connected space, then you require that you also have a multiple intersection. Yeah, but this is a strong condition. Yeah. So when balls intersect pairwise, they also have a common intersection. That is a property of hyperconvex space, and this space have very nice properties, Lipschitz extension property, and so on. The balls that can intersect do intersect in such a space. And so that is the best possible situation. Hyperconvex spaces are tripod spaces, but importantly, in a hyperconvex space, the check complex and the Vietro-Srupps complex coincide because all simplicities are automatically filled. And so for us, this now is a space, is a basic comparison space. And then our idea of curvature is that we no longer look at the deviation from Euclidean space, we look at the deviation from hyperconvex space. That is, we want to see to what extent the Czech and the Vietnamese complex no longer coincide. So of course, in a discrete space, you don't get this intersection, so you need to be a little more liberal. So you need to add some small parameter delta that accounts for the local structure. Otherwise, you can do the same. But these things are also useful for analyzing networks. If you look at the traffic network, you have a couple of distant cities. There are different ways of connecting them. One is just to have one center, connect everything to the center, as in the French railway system. All railway lines go to Paris, yeah, or you connect the distant points individually. And that is precisely the difference between a tripod in the first case, and you connect everything to a center, and kind of a ring structure or circle in the second center. Yeah, and then with this concept, you can evaluate the structure on networks. And so here, I think I'm finishing precisely on time. Here are some of the references for our work. So we have published one book already. Another one will go to print in a few weeks. But of course, we have also put these things on archive. And here you find the code for our scheme if you're interested in that. So thank you very much for your attention.
So the new step of the UMAP is this first step of taking the star graphs and producing this new metric using the star graphs. And so I was wondering if there's some simple continuum limit description of that where the number of points becomes dense. So it'd be something presumably like a conformal transformation with respect to somehow of the probability distribution.
Some, of course, the continuous geometry for me is always in the background. But the point, of course, that was already pointed out, the star graphs do not represent the mutual, the distance between the peripheral points directly. So in contrast to Riemann normal coordinates, you are losing the information about the angles. Yeah. And so, therefore, you do not necessarily get.
So after you unify your star graphs, you get you get a lot of the information.
Yeah,
anyway,
right.
There must be something.
I don't think there's like just think about a surface. Near every point is becoming this tangent point. There's no way to put them together on the surface.
I mean, the basic defining property is that the distance to the kth, the expected distance to the kth point from any point is 1. Once you steal it, that you could have a conformal transformation.
Yeah. I think, well, in the original manifold learning schemes, of course, you shown that is in fact what we worked out in our first book in all mathematical detail. And then you can show if the sampling gets denser and denser, you get convergence because essentially because the Laplace operator, so the random walks converge. Yeah. Here, I mean, as he already pointed out, it's doubtful whether you get anything like that, but we have not carefully investigated that to which extent we get some convergence, for example, of the spectrum of the eigenvalues and eigenfunctions of Laplace type operators. So that would be the natural way to investigate that question. At least that is the standard scheme that has been established so far. But I must admit we have not looked at that, and for reasons that he pointed out, it might be a little doubtful whether they actually do get good results. But I do not know yet.